Our next student is Abigail Dommer, who's a graduate student in the Department of Chemistry and Biochemistry. And her research advisor is Professor Romy Amaro. And I don't know if Romy must be here, but Abigail is up there. She's quick. All right.
Causing an increase in climate and weather disasters. Predicting how the climate will change is extremely difficult, but it's imperative if we want to plan for future disasters and save countless lives. When you think about global warming, you probably think about greenhouse gases. However, these are only a part of the whole story. Clouds significantly modulate the Earth's temperature and actually cool the planet by reflecting solar energy back into space. If you've ever seen your bathroom mirror fog up after a hot shower, then you already know intuitively how clouds form. Hot water vapor hits the cool mirror surface and condenses into, essentially, a liquid cloud droplet. In fact, clouds can only form when there's a surface available. But we obviously don't have bathroom mirrors floating around in the sky to form clouds. So what kind of surface am I talking about? The answer is aerosols. Aerosols are tiny particles like dust and smoke that float around in our atmosphere and seed cloud development. The problem is, not all aerosols form clouds, and we don't really know what makes some better at forming clouds than others. And this makes it impossible for us to include them in our climate models. The largest uncertainty associated with our current predictions comes from sea spray, swirling behind me in blue, which is the focus of my research. Sea spray aerosols contain an enormous amount of chemical complexity, and they're nearly impossible to determine structurally through experiments. So I'm using computers to run the first ever simulations of an entire sea spray particle. Each particle is coated with oils and fats, also known as lipids, which are shown behind me in red. I'm studying these lipids to tease out insights into what drives cloud development. Do the lipids slide across each other like a liquid oil, or do they pack together like solid butter? And most importantly, how might these surfaces interact with incoming water vapor as it gets ready to condense into a cloud droplet? The answers to these questions can be combined with experimental data to improve our predictive models. And this can in turn help us better understand and prepare for the environmental challenges to come, and maybe start to reverse the devastating impacts we already see.